Hello, 8th graders, and welcome to our lesson on linear and nonlinear functions. This is for Chapter 4, Lesson 7 of our math book, and let's get started. So, first off, what I want you to know is by the end of this lesson, you should be able to tell if a function is linear or nonlinear. Lately, in our previous lessons, we've been covering linear functions. Linear functions are functions that if we graph them, they make a straight line on the graph. Now, in this lesson, we're going to start seeing some functions that are not linear, because functions don't have to be linear. Functions can make all different shapes of lines. Now, just a quick review. A linear function is a function that has a rate of change or slope that is constant, which means on a graph, it's going to make a straight line. A nonlinear function is a function in which the rate of change is not constant. So if we had a table, this is what the table for a linear function would look like. We would have it increasing by 2 on the domain side each time and going down by 15 on the range side. So notice it is constant. It's the same on both sides every time. Now, a nonlinear function would look a little different, though. A nonlinear function is going to look a little more like this, where we're adding 3 on the domain each time, but even though we're adding 3 on the domain each time, the range isn't increasing or decreasing at the same rate. So we've got 15, 33, 51. It doesn't have the same each time on the range side. So we know it's non-linear. Let's look at another example. Here's what it might look like on a graph. On a graph, apologize for the sniffing, I've got allergies. Another example here, we've got linear and nonlinear. Now the first one we've got up here is a nonlinear example, because the line it makes has a big old curve in it. So this would be a non-linear example. However, if we look at the graph on the right side, we see that our line is perfectly straight, so this would be an example of a linear function that has been graphed. So a linear function and a non-linear function. Now let's look at an example problem of identifying whether or not a function is linear or nonlinear. So as you can see here, we've got A and B are two different tables, and we're going to identify whether each table is linear or nonlinear function. So here we've got X and Y, our domain and our range, and what we're going to do is we're going to look at each of those and determine whether or not they have a constant rate of change. If they have a constant rate of change, then they're linear. If they don't have a constant rate of change, then they're not linear. So I'm just going to write down the numbers of my first table here, X and Y, 0, 20, 5, 16, 10, 12, 15, 8. Ooh, I need to get a different marker. Now, let's look at what's happening with the domain. Each time here, it looks like I'm adding 5. And on the range, each time it looks like I subtract 4, and subtract 4. So, it looks like I've got minus 4 for my range, and plus 5 is the change in my domain, or my X, and so this is constant, it's the same each time, so this would be a linear function for A. Now let's take a look at B. So here I've written B, and let's start by looking at our domain and seeing how much our change is. We'll see if it's a constant rate of change or not. So we've got plus 2, and plus 2. On my domain or my range, we've got plus 2 here, plus 6 here, and plus looks like 10 here. So you can see that my change in the range is not in accordance with my change in the domain. So I've got plus 2, plus 2, plus 2, plus 6, plus 2, plus 10. So this, because they're not the same on both sides, my domain is staying the same each time, but my range is not staying the same. That means that I've got a non-linear function. Let's take a look at another problem dealing with this idea of nonlinear and linear functions. Tickets to the school dance cost $5 per student. Are the ticket sales a linear function of the number of tickets sold? Explain. This is just like our last problem. We've just got some things to associate our X and Y with. So in this case, we've got number of tickets sold is going to be our domain, and our ticket sales is going to be our range of the function. Now this is a function, we're just trying to decide if it is linear or not. That's what our problem is asking us to do. Are the ticket sales a linear function of the number of tickets sold? Explain. So let's start out by writing down our problem. So here I've got my problem written down. Tickets sold on top, that's our domain, and ticket sales on the bottom, that's our range. And so we've got 1, 5, 2, 10, 3, 15. Now the only thing we have to do is decide if we have a constant rate of change or not. So if I look at my top, I've got plus 1, plus 1. Down here I've got plus 5 and plus 5. Since when this one changes by 1, this one changes by 5, this one changes by 1, this one changes by 5, this would be a linear function. So the ticket sales are a linear function to the numbers of tickets sold. Moving on to our next problem. Our next problem is one I borrowed from Alex and will be in your Alex assignment today. So we've got basically 4 functions here. We've got the first function that's written as a set of ordered pairs, the second function that's also written as a set of ordered pairs, our third function, which is in a table, and our fourth function, which is in a table. So let's take a look at each of these functions one by one. Now, on the ones that are written as a set of ordered pairs, what I'm going to do is write them as a table so that I can more easily check to see if they have a constant rate of change. Here I've written our first function, that set of ordered pairs, but I've written them as a table. So I've got my first pair 2, 0, 3, -3, 4, -6, 5, -9. Now that they're in a table, I can check to see if they have a constant rate of change. So on my domain side, I've got plus 1, plus 1. From here, it was plus 1. From here, I've got went down 3, down 3, down 3. So every time this one changes by 1, this one changes by -3. So this one would be a linear function. Here I've written our second function that we have in our problem. And so our second function says -3, -2, 0, -1, and 3, 0. Then we've got 6 and 1. So we can check the same way. We've got our domain. I'm going up by 3 and up by 3 and adding 3 on that one. This one, it looks like I'm adding 1, adding 1, and adding 1. So every time this one increases by 3, this one increases by 1. So yes, since the rate of change is constant, we've got a linear function. Here's the table of our third function. Our third function is showing us that we've got 1, 3, 5, 3, 9, 3, 13, 3. This one is kind of a unique one that's rather interesting. So if we look at our X side, here I'm adding by 4, and adding by 4, and adding by 4. And on this side, I'm adding 0, and adding 0. What's interesting about this one is if I actually were to graph it on my graph, 1, 3, let's say that's located right about here. 5, 3 would be right about here. 9, 3, 13, 3. what it does is it makes a horizontal straight line. Now, because each domain has exactly one range to go with it, then it is a function, and because it makes a straight line, it is a linear function. And so I've got every time we increase by 4, the other side increases by 0. So this would be a linear function, even though it's kind of an odd one because it makes a horizontal line instead of a slanted line that has a slope. Here I've written function number 4. We've got -2, -4, 2, -2, 6, 2, and 10, 7. So let's check to see if we've got a constant rate of change. From -2 to 2, that's an increase of 4. From 2 to 6 is also an increase of 4, and 6 to 10 is an increase of 4. Now, when I go from -4 to -2, that's an increase of 2. And from -2 to 2 is an increase of 4. And from 2 to 7 is an increase of 5. So when this one increased 4, it increased 2 over here. But when this one increased 4, it increased 4 over here. And increase of 4, increase of 5. So this one would be non-linear. And here's our final problem that we're going to look at today. It says, determine whether the function below is linear or non-linear. And in this case, they haven't given us a table. All they've given us is the equation y equals -4x. However, I can still make a table to see if this is linear or non-linear. So what I'm going to do is I'm just going to make a table down here, and I'm going to go x and y. And if we remember back a few lessons, we learned that the x, or the domain, is an independent variable, meaning it can be any number we want it to be. So I'm just going to put in some random numbers here, 0, 1, 2, 3. It's simple, nice and small. And I could put these in because the domain is independent, meaning I can have it be any number I want. So I just chose some numbers, 0, 1, 2, and 3. Now, the y is a dependent variable because it has to follow what the equation says. So now that I've said x is 0, if I plug 0 in for x up here, 4 divided by 0 is going to get me 0. Or I should say -4 divided by 0 is going to get me 0. Now, if I do -4 divided by 1, well, that's going to get me, I believe, -4. And if I do -4 divided by 2, well, that's going to get me -2. And if I do -4 divided by 3, well, that's going to probably get me something really funky. It's going to get me repeating decimal, like I think it's like 1.3 repeating. So, oh, and it would be negative. So looking at this, I've increased by 1, increased by 1, increased by 1. And on this side, I've gone down by 4, increased by 2. And I've increased by, what's that, like 0.7? That shows me that this would be a non-linear function. Okay, so you can see that even if they give it to me in equation form, I can create a table and find my input, which is whatever I want it to be, 0, 1, 2, 3, -1, 0, 1, whatever numbers I want to choose, 10, 20, 30, doesn't really matter. And then on this side, I'm going to get my outputs based on the equation and how this domain fits into it and what it causes me to get for the y. So that is our lesson on determining whether a function is linear or nonlinear. Hope you enjoyed it, and we'll catch you next time.